Now let us understand Hooke's law clearly using this simulation. In this simulation, we can see a specimen fixed at one end, and a load applied gradually at the other end. As the load increases step by step, we observe that the elongation of the material also increases. Initially, for small increments of load, the extension is directly proportional to the applied load. This means if we double the load, the extension also doubles. This linear behavior confirms Hooke's law, which states that stress is directly proportional to strain within a certain limit. On the graph shown in the simulation, this region appears as a straight line passing through the origin. This straight line portion represents the proportionality limit. Up to this point, Hooke's law is valid. The material behaves perfectly elastically, and the slope of the line represents the modulus of elasticity. As the load is increased further, we reach a point where the graph starts deviating from the straight line. This indicates that stress and strain are no longer proportional. However, the material may still return to its original length if the load is removed. This region is called the elastic limit. So between proportional limit right arrow Hooke's law is valid. Elastic limit right arrow elastic behavior exists, but Hooke's law does not strictly apply. Beyond the elastic limit, when the load is increased further, the material undergoes permanent deformation. If the load is removed in this region, the specimen does not return to its original shape. This clearly shows that Hooke's law exists only up to the proportional limit. Elastic behavior exists up to the elastic limit. Beyond elastic limit, plastic deformation begins. This simulation clearly demonstrates the relationship between load, extension, proportionality limit, and elastic limit, helping us visualize where Hooke's law is applicable in real materials.